This video is the second of two, which are replacements for lecture for Math 361 on September 26, 2022. Okay, so in the previous video, I went over a few of the examples that we've seen in class and one that I added in without going through the details. Here I'm going to go through the details, and hopefully this is helpful for working on the Hulk banner problem in the homework assignment, because it has some similar features, but it is a more complicated case. And what I also want to illustrate is what happens with the mean or the expected equations when you have what we call a bimolecular reaction. Bimolecular meaning two different things have to find each other and, let's say, bind together to react. But really this phenomenon that I'm going to point out is general whenever you have a rate that depends on two things finding each other. Okay, so what we're going to do is we're going to try and write down the KFEs for this and then the expected value for the process. And so we have to decide how many things we start with. So we'll have N of type A. So there's going to be N of protein A, this little C-shaped thing. And we'll have M of type B proteins. That's this one here. And we'll start off with none of these. So the reaction initially will go completely forward, but then it'll start to balance out. Okay, let's just for, it doesn't really change anything, but just for being able to work with specific cases, let's assume that N is greater than M. If you write it down in a slightly different way and you realize that M is bigger than N, then you just swap them in this calculation. All right, so we could have 0 C's at the beginning, but then with some binding happening, we could get 1 C or 2 C's. The maximum number of C's we can get out of this, because we require the smaller number B, M of the B's, we can never have more than M of the C's. So that's as high as we're going to go here. So we have M plus 1 states that we're transitioning between. Okay, so in the notes that I'll put on the course website, I'm going to put in some comments about KB and KU for general interest. They're a little bit technical and they're a little bit hand wavy, so I won't go through those here. But it may be interesting if you're interested in these types of models to read through that just to get a better idea of how those parameters are interpreted. Okay, so let's write down the probabilities. So we have Pn of t are the probabilities that we have x of t is equal to n, where x of t is the number of c's. And they're called complexes, a combination of two proteins bound together. And so what we like to do is write down the Kolmogorov equations for this. And to save a little bit of time doing this, I'm actually just going to go directly to the equation, and hopefully you can start seeing how the equations are derived and what you end up with in the end. So I will write down dpn dt and just give some kind of hand wavers for how this comes out of the type of derivation that I did in class. So we have a term that comes from the probability of there having been n minus 1 C molecules before, and when there's n minus 1 of them, we move forward at a rate kb, and there are, now how many different possible ways are there of moving forward from n minus 1 complexes to n complexes? Well, we have to count up the A's and the B's. So there are n minus 1 type A molecules, and there are m minus n minus 1 B molecules. And those are all the possible ways that I can have two of the A's and B's present combined to make a C, and those all happen with a rate KB. So if you go through from the plus delta t kind of derivation, this is a term that should appear somewhere in your calculation early on. Okay, and then we lose them from the nth state by two ways, binding and an unbinding reaction. So there are n possible ways that C complexes, n of them, can unbind from each other. And so that happens at a rate Ku. And then we have Pn. You could also have two of them bind to move up to Pn plus 1, and that happens at a rate, how many A's are there when there are n C's? There are n minus n A's. And how many B's are there? There are m minus n B's, and they bind at a rate Kb. And finally, we have the possibility that we had n plus 1 complexes, and one of them fell apart. Well, if there's n plus 1 of them, then we have n plus 1 different ways for them to fall apart, and they do so with a rate Ku. Okay, so I'm just going to annotate this with a little comment here. When n is equal to 0, this term here doesn't make sense because there are no states to the left from which it might come. So this term is only here when n is not equal to 0. And this last term is only here when n is not equal to capital M. You have as many C's as possible. So those two equations, this is m plus 1 equations represented here with just the subscript n, but the very first one for n equal 1 and the very last one for n equal capital M have extra terms that we should ignore, each one here and here. All right, so that is the Kolmogorov Forward Equation. And at some point, you should be able to sort of write these down without going through the whole process because they kind of make sense on their own. And this is what we're going to continue doing through the term. Actually, we're not going to write down the Pn equations. We're going to jump straight to the y equations. And so what is the equation here for y? Well, y is the sum. In this case, we're going from n equal 0 to m of n times Pn. And when we take a derivative, we get the sum from n equals 0 to m of nPn prime. And we can now drop in the equation here, the right-hand side of the Pn equation. And you'll notice this equation starts from n equals 0 and it goes all the way up to m. So in this sum, when we're at 0, we have to omit this term, and when we're at m, we have to omit this term. But I'll write it down just as the whole formula for now. So this is Pn minus 1, n minus n minus 1 times m minus n minus 1 times K binding minus Pn n times K unbinding minus Pn n minus n m minus n times K binding plus Pn plus 1 times n plus 1 K unbinding. And let's just keep in mind that if we ever see an n equals 0, meaning a p minus 1 or a pm plus 1, we just have to ignore those because those are 0. Okay, so as we saw in class, the trick here is to break up the sums and shift any that have the wrong subscript so that we have all of the p expressions as Pn. That's what we would like. So I'm going to write down I'll squish this over as far as I can for room. So this is still y prime equal, and we get a sum from n equals 0 to m of n times pn minus 1, n minus n minus 1, m minus n minus 1, kb, plus the sum from n equals 0 to m of, oh, I see, that should be a minus here, so let's change that to a minus sign right here. And then sum from n equal 1 to m of n from out front here, multiplied by this expression here. So we get n squared times p n ku, and then minus the sum from n equals 0 to m of, now we have n times n minus n, m minus n, p n kb, and then the last one is plus the sum from n equals 0 to m of p n plus 1 times n plus 1. Oh, I forgot the n in there, so there's multiplied by n from out front again of the whole sum at the beginning here, this one here. And so let's see, pn and then multiplied by ku. Now, remember I said if we ever have minus p minus 1 or a pm plus 1, we can ignore those. So what that means here is that this n equals 0, we shouldn't start from 0 because this term here would be a 0. P minus 1 would be 0. It doesn't make sense to talk about that one. So this should be starting from n equal 1 instead. And the same idea holds here when I'm at m. This pm plus 1 doesn't make any sense because we can't possibly, it's impossible to have m plus 1 complexes. So this one should be m minus 1. Okay, now we shift our indices. So the middle two sums are fine. They have a pn expression. But this expression here, we'd like to have that be p sub n, and this one we'd like it to be p sub n. And then we'll be able to see anything of the form, for example, n p sub n, which corresponds to y, the original expected value. Okay, so the shift, what are we going to do to shift? What was n minus 1 has to become n now. So let's say n equal 1 would now be n equals 0. So if I write down n equals 0, and n equal capital M would have to go also down by 1. So I've now shifted from 0 to m minus 1. And now the n value is going to be n plus 1, p n. And this one is n minus, well, n minus 1 becomes n, and m becomes n, and you have a kb at the end here. Okay, so let's just check that we got that right. What do I mean by got it right? So when n was equal to 1 in this expression, we want to have all the right pieces. So when n is equal to 1, we want a 1 here. Well, when n is equal to 0, we have 1 there, so that's the same expression. When n is equal to 1, we have p0, and when n is equal to 0, we have p0. So far the first term is looking correct. When n is equal to 1, this is n, capital N minus 0, which is capital N. And here it's n minus 0, which is capital N. So we have capital N for the first term, capital N, and the same thing for this term here. So that shift worked correctly. Okay, so then we can fill in the others. Sum from n equals 0 to m of n squared pn ku, and minus the sum from n equals 0 to m of, now here, yeah, we're okay here because the subscript is pn, so there's no shifting to do. And this one we're shifting the other direction, so n's become n minus 1's, and the summing index goes in the opposite direction. So before a 1 became a 0, now a 0 becomes a 1. and we're going all the way up to m. And the subscript on the p becomes pn. So you can see here what we had is p with n equals 0, this is p1. With n equal 1, this is p1. Great, that's the same piece. That's the same term in that expression. The n plus 1 just becomes an n, and the n becomes an n minus 1, and multiplied by ku. Okay, so what overlap do we have here? You'll notice that we have a ku and a ku multiplied by pn and an n squared in front. And here we have an nn minus 1. There's an n squared with a plus sign in front and a minus sign in front. So this whole term here cancels out with the n part of that whole expression, but we're left with the minus 1 part. Okay, so that's one piece. And then the other thing that cancels out here is the kb terms. We have, I have to be a little bit more careful. So this one went from 0 to m, and this one went from 1 to m, but the difference between those is just the 0. But when I plug in the 0 here, it's just 0 because there's an n squared. So it doesn't matter that they're different in the indices because the only term that I have here that isn't here is actually a 0. And the same thing is going to happen in this expression. Well, we don't have a difference. Oh yeah, we do have a difference in the index here. So that we have to be a little bit careful about. Because when we plug in capital M into this, oh yeah, there it is. It's 0. So this m minus 1 could be m, and it wouldn't make a difference. So the same thing happens in this term. And so what's going to cancel now? Well, we have an n multiplied by pn, n minus n, m minus m, kb. So that n term is going to cancel. I'll put the slash the other way so we know which one goes with which. And that covers this whole term here. And then what we're left with is just the pn, n minus m, n minus n, m minus m, m minus n kb. So let's write that down. So here we have what's left. We have the sum from n equals 0 to, now we can make this to m or m minus 1, but because the expected value has a formula with the m in it, I'm going to add the m. Why does that not change anything? Because this term right here, m minus n, is 0 when little n is equal to m. So it'll just be a 0 term, and we added 0 to our sum, no difference. So this is kb times pn. And you'll notice I'm migrating those p-values slowly to the end of my terms because usually I put coefficients to the left and the functions to the right, but it's not too big a deal. And then what's left? We have to add to that the sum from n equal, now I can start from 1 to m, but my original expected value up here was going from n equals 0 to m. I'm just going to add in the 0 term, and in this case that doesn't change anything again because n equals 0 makes this term that I just added 0. Now if I don't have a 0 term, like if I have to put in something like a 0 here, but there wasn't a 0 in there so it didn't become a 0 term, then I would have to subtract off that term at the end. And sometimes, you might have to do that. But in this case, all the examples here where we've changed the indices always correspond to adding a 0 term. Okay, so what do we have left? We have, now first of all, there's a minus sign in front because the minus sign in front of the 1. And then we have n times k unbinding multiplied by pn. And now we can see some familiar terms, at least at the end there. This one, this first term is not super familiar, but I will rewrite it multiplied out. And you can see that this is the sum from n equals 0 to m of nm minus n plus m multiplied by little n plus n squared kbpn minus, and this is just ku multiplied by y of t. So now we have to figure out what this expression here is. And it's a slightly complicated term. So let's go to the next page here. Oh, maybe I'll copy it over. So we're still writing down a y prime expression. So I'll add that in here just to remember. Y prime is equal to so now we're going to rewrite this in separate sums. So we're going to have the sum from n equals 0 to m, to capital M of nm kbpn minus the sum from n equals 0 to m of n plus m times n kbpn plus the sum from n equals 0 to m of n squared kbpn minus ku times y. All right, so this first term, I can factor out the n and the m are just fixed constants, as is kb. So we have the sum from n equals 0 to capital M of pn. Well, that's a total probability. So this is just 1. This expression here is just 1. So I'll replace that with a 1 in a second. This one I can also factor a bunch of stuff out. N plus m times kb. And then I'm left with, you can see here, the sum over all states of n times pn. That is, again, just y. And then we have plus the sum from n equals 0 to capital M of n squared kb pn. Okay, so let's just clean that up a little bit. We have n times m kb, and this term here is just 1. And then we have minus n plus m kby plus, oh, I've forgotten a term, didn't I? I forgot the ku times y. Minus k unbinding times y. And now this one we have summation of n, well, I can factor out some terms. So let's factor out just the kb. Summation from n equals 0 to m of n squared pn minus kuy. So here is where we are starting to see something different than what we've seen before. And that's because this is what we call a bimolecular reaction. You'll notice that this expression here, the nm kb minus n plus m kby, looks like the first two terms of a squared expression. And so we can add and subtract in a term. So first of all, I'll factor out a kb. And then we can add and subtract in a term. So we have nm minus n plus m, n plus my plus y squared. But now that y squared was not there before, so I would subtract it back out. And now this part of it is a product of two terms that kind of look like the product that we had earlier. And then we have some extra stuff, plus kb sum from n equals 0 to m of n squared p sub n minus kuy. And now what we can do is we can write this first term as n minus y times m minus y. That's these three terms. And then we're going to group this minus y squared times kb with this expression here. So we get plus Kb multiplied by the sum from n equals 0 to m of n squared Pn minus y squared minus Ku times y. Now, hopefully this expression is familiar right here. This is just the variance of n. So let me write down as a reminder what the variance of n is, or the variance, I guess, of x of t. So we have the sum from n equals 0 to capital M of n minus the expected value of n, all multiplied by the nth probability. Squared. Right? It's the squared of your variable minus, or your state minus the expected state, squared multiplied by the probability of that state. Okay, so if you write this out, multiply it out, you get the sum from n equals 0 to m of n squared minus 2n sum n Pn plus sum n Pn all squared times Pn. And in here, you can, well, now you can separate these out and you get the sum from n equals 0 to m of n squared Pn minus, now this is just a constant, well, changes in time, but it's a constant with respect to n. And so this is really, when I take the sum and distribute it over to here, and I get the Pn multiplying it, this is really minus 2 times the sum of n Pn squared, because there's two of them there. And then the last term is plus, now this one is just y squared. And so when I add up the sum over all the probabilities multiplied by y squared, the sum of all the probabilities is just 1. This is independent of n. And so I'm just left with y squared. And this term is also y squared. So what I'm left with is sum from n equals 0 to m of n squared Pn. I'm subtracting 2 y squareds and adding 1, so that's just minus y squared. So this expression here is exactly what we had here, and that's just the variance of the stochastic process. So what we have is the expected value prime, the derivative of the expected value, is equal to Kb times the number of A molecules times the number of B molecules minus Ku times the number of C molecules plus Kb times the variance of x of t. Now, typically when you have a forward reaction like this one, that involves two proteins or two objects coming together and finding each other, people will say that the rate is, so now if I write this down in terms of concentration, usually people will write down C prime for the number of, the concentration of complexes C is equal to Kb times the concentration of A's times the concentration of B's minus the unbinding rate multiplied by C. In other words, the forward rate is just the product of the molecule numbers, or once you switch to concentration, it's the product of the concentrations. And the backward rate is just like we had for all the other things where you have radioactive decay, or in this case, protein breaking apart. So you get something proportional to the concentration C. But we have this extra term in this expression that people usually omit, and we need some justification for doing that. So there's two different cases that we could be in. One is where M and N are large, and we have a lot of A's, B's, and C's typically in the regimes where we're interested in writing down these equations, in which case this variance becomes smaller and smaller. And that's because the variance will be growing like square root n, even though the number of molecules grows like n. And so I won't go into the details of that, but generally people trust that they can just ignore this term because the variances will be small relative to the concentrations or the number of molecules involved, and they can ignore it. But if that's not the case, if you're looking at reactions at low numbers, then you would have to include this, and then what you need to do is find an equation. So maybe you call this variance Z of t, and then you need an equation for the variance. And that would take a lot more work, and people tend not to do anything like that. So this is the type of equation that people would typically write down for a bimolecular forward reaction with a unimolecular backward reaction. Okay, so that is another more complicated example than anything we've seen, and more complicated than anything I would expect you to work through, but it has some pieces in it that are relevant to the Hulk problem, which is to say you have a finite number of states and you have forward and backward rates for each one, which is something that we haven't seen in the previous cases.